Lesson 6-3 Similar Figures and Scale Drawings. Alright, so yesterday we learned how to make proportions. Today we're going to talk about using those proportions to solve for similar figures. Similar figures, like you can see these two triangles here, they may be similar, meaning they look the same, but they do not have the same shape. One triangle is clearly smaller than the other. The important thing to note about similar figures is even though they're a different size, their angle measures, 64, 61, 55, are the same no matter the size of the shape. The other interesting thing is their sides, so side AB, corresponds to XY. So 12.4 might not equal 8.3, but all of their side lengths in comparison should be in proportion. Alright, so we're going to use this example to solve for a missing side in our parallelogram. We have two parallelograms. They're different, they're similar, but they're not the same size. So side AB here corresponds to side EF. This side length is 16, this side length is 24. Side AD corresponds with side EH. You can see we're missing the length for AD, but we have the length for EH. So we can solve this missing side by writing a proportion for the corresponding sides. You want to be really sure you're setting up your proportions correctly. Now, you can do this one of two ways. I'm going to write my ratio from little parallelogram to big parallelogram, meaning for my first side, I know 16 corresponds to 24. 16 to 24. Set that equal to little parallelogram to big parallelogram. You want to do the same thing you did for your first ratio. So this one will be x to 18. I have the side lengths of my small parallelograms on top and my large ones on bottom. Now I can solve this proportion using cross products. 16 times 18 is 288. 24 times x, divide by 24, x equals 12. 12 is my missing side length of my parallelogram. Alright, let's do a couple more practice. Here are we have two figures here, and we're not sure if they're similar, so we need to solve their proportions to see. Alright, so I'm going to do big rectangle to little. Oh, well, let's see. I already have something written, so let's go little rectangle to big. So 4 to 6 equals bottom of little to bottom of big. 3 to 4. Let's see if these are in proportion. 4 times 4 is 16, whereas 6 times 3 is 18. These side lengths, those rectangles are not similar because their side lengths do not correspond in a proportion. Alright, let's try the triangles. I'm going to do this long side to this big side. So 6 to 60 equals bottom of little to bottom of big. 5 to 10. Alright, well I already know this is not going to be proportionate because 6 times 10 is 60 and 6 times 5 is 300. So that is not proportionate. Last one. This one's tricky because this little triangle is turned. So if we highlight corresponding sides, this long side here that's opposite this right angle is actually this side down here. So if I write a ratio for little to big, it's 6 to 9, set equal to my long side 4, which is actually with this 6. 4 to 6. Well, 6 times 6 is 36, and 4 times 9 is 36. These are similar triangles because their proportions equal each other. Alright, you can also solve for similar figures to find distances that are difficult to measure, and doing this we call indirect measurement. It's basically like similar figures. So if I have a tree here and it casts a shadow so here's my tree and it casts a 10-foot long shadow. And then I have a 5-foot woman standing next to the tree. Her shadow is only 4 feet. See how we kind of, with a dotted line, made these look like a triangle? I can solve if I wanted to know the height of the tree because I know the height of the woman and her shadow, and I know the height of the tree shadow. I can solve for this missing length. So I'm going to set up a proportion. I'm going to go height to shadow, height to shadow. So the woman's height is 5 and her shadow is 4. The tree's height we don't know, but its shadow is 10. Cross multiply, 4x equals 5 times 10 is 50. And if I do, I'm just going to get this exact answer. If I do 50 divided by 4, I get 12x equals 12.5 feet. So the tree's height is 12.5. All right. And finally, we can use our similar figures and our proportions to do something similar with a scale drawing. So a scale drawing we see all the time. It's an enlarged or reduced drawing that is similar to an actual object or place. So a lot of times when we look at a map, it gives us a scale for distance. In other words, the scale of this map is for every 1 inch you measure on the map, it equals 44 miles in the real world. So we can use this scale to find out how far a distance actually is. So you want to start by, we want to find the distance from Sacramento to San Rosa. So it looks like they're measuring the distance right here, and it looks like it's about 1.5 inches. So set your proportion up with your scale first, what they give you. 1 inch is to 44 miles. We're going to set that equal to, well, we just measured 1.5 inches. What is our distance going to be if we want to go from Santa Rosa to Sacramento? So that's our variable goes here. We're going to cross multiply. 44 times 1.5 equals 66. 1 times x, divide by 1, x equals 66 miles. All right, these are the 3 problems I would like you to try. The first problem is solving for a missing side length in those similar parallelograms. Problem 2 is indirect measurement, looking at a building's height and shadow. And problem 3 is using the same scale factor from the last problem, 1 inch equals 44 miles, to solve for the distance on their map. Good luck!